Arizona Science is supported by Research Corporation for Science Advancement.
For AZPM, I'm Leslie Tolbert, Regents Professor Emerita in Neuroscience at the University of Arizona, and this is Arizona Science. Our guest today is Bryan Black, Associate Professor in the Laboratory of Tree Ring Research at the University of Arizona. Bryan uses tree ring analysis techniques in novel ways to study long-term changes in aquatic creatures. Welcome, Bryan.
Thank you.
What features are you measuring, and how is it telling you about changes over time in, say, coral reefs?
At first, I was amazed to learn that so many organisms form annual rings and live a long time, just like trees do. And I originally got my start looking at rockfish, which are long-lived genus of fish that are common from California on up through the Gulf of Alaska and can live over 100 years. I think the oldest rockfish that's ever been aged is over 200 years old.
Oh my.
So a very slow-growing, long-lived species. And they form rings in a structure in their head called an otolith, oto for ear and lith for stone. And as the fish grows in size, that growth is reflected in the width of the growth increments within the otolith. And so we thin section those, put them under the microscope, and then we can resolve those increments. And in fact, the cross sections from an otolith look very similar to the cross-section of a tree, like a tree stump.
So you'll have wider rings in some years and narrower rings in other years?
That's right. And so the width reflects the growth of that fish, and that wide widths indicate favorable growth years that fish experienced. And then, of course, the narrow rings tell us about the years that the fish had less growth.
So how do you then go about matching the timeline that you can decipher from these fish bones to human activity in the marine environment?
Well, the first big thing is to establish the relationship between the fish and climate. So temperature or indices of productivity on the west coast of the U.S., it's a phenomenon known as upwelling, and temperature, and compare them to the fish records. And what we find is that wintertime conditions are quite critical for fish growth, because during the summer and spring, there's always a lot of this upwelling and productivity, but winters can be boom or bust. And the fish are very sensitive to that. And we can even link those fish chronologies to indices of seabird reproductive success that have been collected for the past 30 or 40 years and show that synchrony with the fish and the birds, and that they too are sensitive to wintertime climate. And then this informs managers that, in fact, it's wintertime climate that's inducing variability in growth of the fish, and that we see it in other indicators at the top of the food web, and that wintertime is important. So we will expect to see that pattern in fish growth over time.
So you're learning actually a lot about climate change through this analysis of the fish bones.
That's right. We do see climate change signals. And off California, for example, with this wintertime climate that imprints fish so strongly, and seabirds and other indicators of plankton, for example, what we find is that variability in wintertime is increasing, that we're having climate whiplash, that upwelling is becoming more boom or bust over time, and that the same atmospheric phenomena that control upwelling also control the amount of precipitation received on land. So it turns out that tree ring chronologies that are sensitive to how much precipitation is received relate quite strongly to the fish chronologies. And because the trees live so much longer, then we can hindcast this climate, wintertime climate, several centuries into the past. And we find again that climate volatility is increasing and has been over the last few decades. And then we continue to see that in the instrumental records, and that Earth system models also suggest that this pattern of volatility will increase in the future. So these linkages we can make across fish, trees, other records are all enabled by this fundamental process of cross-dating and making sure that everything's exactly dated and placed correctly in time, which allows a seamless integration across physical and biological variables.
Thank you very much, Bryan, for this glimpse into a really surprising application of tree ring analysis. Bryan Black is an expert in applying high-end technologies to studying changes in climate and the impacts of those changes on living systems.
Thank you.
You can listen to this and all Arizona Science conversations at azpm.org/Arizona Science. I'm Leslie Tolbert.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science.